స్కూల్లో కమ్యూనికేట్. So let that be known to others. So they'll also get benefited from the coaching. And students, you will have, see, you will require some books, right? When books, ever under the books, like good books I'm talking about. I'm not talking about just intermediate books. I'm talking about books for competitive exams. Shivani, Likita, Ashrita, Gayatri and Vignesh, I know you have books.
Yes, sir.
You have already. Which book are you following, Ashrita?
Sir, in my college, they gave, sir.
They gave you material? All right. All right.
Yes, sir.
All right. So, ఆ book చేస్తున్నారా మరి మీరు?
Yes, sir.
So, what is going on in your class? Physics లో ఏం జరుగుతుంది ఇప్పుడు?
Loss of motion, sir.
ఓ, లాస్ ఆఫ్ మోషన్ జరుగుతుంది. ఓకే. ఇంకా ఆల్ రైట్. ఓకే. లిఖిత మీ కాలేజ్ ఏం జరుగుతుంది ఫిజిక్స్ లో?
Fluids, sir.
సారీ?
Fluids, sir. Mechanical properties of fluids.
Fluids. All right. Fluids. All right. Okay. Vignesh, what is going on in your class? Vignesh, Gayatri, and Shivani, what is going on in your class? Your chemistry class will start in 2 minutes.
Oscillation, sir.
Okay. Work, energy, and power. Gayatri says work, energy, and power. And Vignesh, what is going on in your class?
Oscillation, sir.
Oscillations. All right. Okay. So, ఈ హాలిడేస్ వస్తున్నాయి కదా, I should make best use of the time. All right. హాలిడేస్ కాబట్టి let us relax a bit. ఎందుకంటే మార్నింగ్ ఈవినింగ్ క్లాసెస్ you'll have anyway. బట్ క్లాసెస్ తో పాటు ఇప్పుడు మీకు కాలేజ్ ఉంటుంది కాబట్టి టైం ఎక్కువ ఉంటుంది ప్రాక్టీస్ కోసం. సో డివోట్ ఫాలో ద టైం ఫర్ కాంపిటేటివ్ ఎగ్జామ్స్ ప్రాక్టీస్ కోసమే డివోట్ చేయండి. రైట్. ఇంటర్మీడియట్ కాలేజ్ ఉండదు కాబట్టి ఆ టైం మీరు మొత్తం ప్రాక్టీస్ కోసం డైరెక్ట్ చేయండి. రైట్. శివాని ఆల్సో సేస్ వర్క్, ఎనర్జీ అండ్ పవర్. ఆల్ రైట్. Who else we have here? All right. Madam has joined. Good morning, ma'am.
Good morning, sir.
Ma'am, you may please continue, ma'am.
Sir, please wait. Yes, sir, ready. Sir, should I start?
Please, ma'am, please start, ma'am.
So, hello students, good morning. So, last class we were doing different sums. So, does anyone have any problem with the sums? Solving with the sums, was everything clear to you? Yes or no? Today we will be starting with the cyclic process. Okay. So before starting with the cyclic process, so do you know what is the cyclic process? Okay, let's start. My screen is visible to everyone.
Yes, ma'am.
So so I guess the sums were clear to you. Right, so let's start with the cyclic process today. Yeah. So does anyone have any idea what is the cyclic process? So for the this cyclic process, first we will be learning with starting with the sign convention. So anti-clockwise work is always taken as positive and the clockwise work will be always be taken as negative. Because in anti-clockwise work, the expansion occurs at low pressure and compression occurs at high pressure. This is the standard convention. So what I have told, anti-clockwise work is always taken as positive and the clockwise work is always taken as negative. Okay, because in the anti-clockwise work, expansion occurs. Okay, expansion occurs here. And in the clockwise work, compression occurs. Okay, this is the basic difference. So compression usually occurs at high pressure. So this is the standard. So from first law of the thermodynamics. And this U is 0. Okay. We already know that I have told you like for millions of times that U is equivalent to 0 for the first law of the thermodynamics. Thus we can say like this, yes or no. Okay, so this is the standard formula for cyclic process. Remember, in case of the standard process like the isobaric, isochoric, isothermal, we can directly use the formula. But if the pressure is not standard, then we will use a different formula. So what I said, this is an important point to note. In case of standard process, like isobaric, isochoric, and isothermal, we can directly use this formula. Use the formula. But if the process is not standard, then we will be using this formula. Okay, so if the process is standard, we will be using Q is equals to minus of W. But if the work done is not standard, we will be using this formula. Is this part clear? So let's do a sum. Let's do a sum. This is this is one of the previous year question of IIT. Mostly JEE at JEE mains, I guess. Try to solve this sum, then we will move to the next sum. Just try for once. I will give you exactly 2 minutes to do. Just try for 2 minutes. Okay. So let's start. So what it is being said here that the process is for, so what is being given in our question? I'm writing it here. What it is already given in the question. It is given that the process is for 1 mole of the ideal gas, right? 1 mole of ideal gas. Second, total heat released, which is Q. Q is equals to minus of 600 calories. Why is the negative sign? Negative sign indicates that the heat is released. Remember the first class that if the heat is being released, then we use the negative sign. Negative sign as heat is released. Okay, so, and this process is adiabatic. Now, how did so if the process is adiabatic, so there will be no exchange of the heat with the surroundings. In the question, is there written that there is heat exchange with the surrounding? No, right? So, we can consider this process to be an adiabatic. Okay? Because no exchange of the heat with the surroundings. So is this part clear what it has been given in the question? Yes or no?
Yes, ma'am.
Ma'am, once last point, can you explain again?
The last part.
Yes, point, ma'am.
Adiabatic means there is no heat transfer between the system and its surrounding. In this problem, it is stated that the process is adiabatic, which means that no heat is added to or removed from the gas during the process. Okay, there is heat is released, but not the exchange with the surroundings. So we are writing it to be an adiabatic process. Is this part clear? Is this part clear or not?
Yes, ma'am.
Okay, so what has been given in the question, always write that first. Okay, so wait. One more thing you can do, that since heat is written like this, that 600 calories heat is released, so you can just omit this point also. If this comes to be like this, you can omit this part of the question also and just casually think that no, this is not an adiabatic process. Okay, you can do like that also. Now a PV, and now this is what, this is a PV diagram. Okay, so and we already know that temperature for this part is given to be as 300 Kelvin, and this part is given to be as 400 Kelvin. Okay, so first we will be doing that adiabatic process. Since Q is equals to 0 for an adiabatic process, according to the first let's do with the, then I will be explaining to you with this point. Okay, first let's do with this adiabatic one. Let me explain. Suppose you have forgotten this point. Okay, let's just forget up to this point. Now we will not consider this. Let's first focus on the adiabatic process. Suppose this part was not written. Okay, if this part was not written, then how we have solved it? Okay, so we know that the adiabatic process, that Q equals to 0 is adiabatic means no heat exchange. So Q will be 0. So Q is 0 for an adiabatic process. So by the first law of the thermodynamics, so for adiabatic process, Q is equals to 0. So according to the first law of the thermodynamics, not Q, U becomes equal to W. Okay, because U is equals to Q plus W, Q is 0, so U is equals to W, and it will be the change of the internal energy. So U is the change in the internal energy and W is the work done. So for an ideal gas, now it is said that it is for an ideal gas. So for an ideal gas, change in the internal energy is given as 3/2 N R delta of T. Okay, so N is given as 1 mole. It is said that N is 1 mole of an ideal gas. Wait. So N is 1 mole of an ideal gas, which is already given in the question. R is our gas constant. What is the value of R? Last class I told you.
8.314.
Yes, 8.314. Then delta T. Delta T is 400 and 300 of negative. So that is 100. So what will be the work done? See, we already know U and we already know that W is equivalent to work done. So what will be the formula? 3 by 2 into 1 mole, 8.314 joule per mole. Joule per mole Kelvin into 100 kelvins. So whatever you will get, that will be your answer. Okay, so if you want something, you will be getting in joule. Now you know that 1 calorie. To convert joule into calorie, 1 calorie is equivalent to 4.18 joules. So accordingly, whatever joules you are getting, you can calculate that in calorie. Okay. Up to this, is this clear?
Yes, ma'am.
Anyone, any doubt?
No, ma'am.
Okay. Now, this is the kind of the question you will be getting. Now, this is something I told you that if this part was not given, okay, this was the question, but this part was not given. Now, let's just solve if this part was given. Everyone has copied this or taken a screenshot of this.
Yes, ma'am.
Ma'am.
Everything will be same, just this part will be omitted. Now, I'm then erasing it. Okay. What is given? 1 mole of an ideal gas. And what is the heat exchange? Q. Q is 600 calorie. Because negative sign will be given because heat is being released. What is the initial temperature? It is 300 kelvins. And what is the final temperature? It is 400 Kelvin. Up to this, clear or not? Yes or no?
Ma'am, can you tell me what is for 300 Kelvin?
Yeah, say it clearly. I can't hear you.
What is for 300 Kelvin, ma'am?
I said that the heat is being released. So I am giving here the negative sign. And 1 mole of an ideal gas, it is already given in the question. What is your initial temperature? Among these three, you have to calculate for here. What is the initial temperature in this question, in the whole question?
300 Kelvin.
Yeah, what is the final temperature?
100 Kelvin, ma'am.
Yes, not the final temperature, that is the heat exchange, right? But initial temperature is 300. Final is 400. So the heat exchange is 100. Is this part clear?
Yes, ma'am.
Okay. So now let's do the internal energy part. So what will be the formula for delta U? Delta U will be 3 by 2 NR of delta T. Why I am using this formula? Because it is being said for an ideal. So for ideal gas, you can use this formula. So into 8.314 joule per mole Kelvin into 100 Kelvin. So whatever you are getting, That will be around, calculate and tell me. Something in Joule. Now, according, yes,
147.1 joule.
47. Okay. Now, what will be the work done? Work done is equals to Q minus delta U. Yes or no? What is the general formula? U is equals to Q plus W. I have just exchanged the signs and have written like this. So is this part clear?
Yes, ma'am.
Good. If you just convert it into calorie, you can do it. So that will be around minus 600 calories because here it is written in calorie. So how much calorie is this? Last time I just told you, so just calculate it, how much calorie is this? Or you just can simply convert this calorie into joule. So this is 600 calorie into 4.184. Yes, 4.184 joule per calorie. So this is how you convert it to calorie, 1247 joules. Okay, so something like minus 3931 joule. So the work done is approximately negative of 3931 joule. See, the negative here indicates that the work is done on the gas. This makes sense because the gas is releasing heat, losing energy, temperature is increasing. So suggesting that the work is being done to compress the gas. Is this clear to everyone? Is this clear, everyone?
Yes, ma'am.
Ma'am,
Okay.
ma'am,
Yeah, say.
have you converted 600 calorie into joules?
Yes, yes. 1 calorie is approximately 4.18 joule. Okay. So I've just done that. Done? Okay. So if this is clear to you, let's do another sum of similar type. Here, the question will be
Ma'am,
directly given. Yeah, say.
if we have converted 600 calories into joules,
Yes, you can do it in joules because here the something is written in calorie and it is easy to convert calorie to joules. So I have done that. You can do it in joules, in calories also. No
yeah,
problem.
ma'am, then it will be 2005, 511 or
Yeah, whatever
510
it is.
approx.
Whatever it is, Karl.
And then answer will be 1 to 4 number. It will be 2630.
Yes, approximately that will come. See, here what is more important? Here the negative sign is important. Negative sign means what? Work is done on the gas. And you can see here the heat is being released also. See, if this is gas, okay, and someone is pressing this gas down. So obviously some heat will be released. So that is, you are getting something in negative sense. So obviously this also makes you think correct. Okay. So something when it is said that the heat is released, you will see that you are getting the work done in negative side. Okay.
Yes, ma'am.
Okay. So let's do another sum. So again, calculate the work done like this. Are you practicing the sums at home? The numericals from your book.
Yes, ma'am.
Good. If anything you can't solve, please ask me. Please. Okay. This we are solving, this we will solve using the alphabets. One by E square. This is PV graph. This will be 1 by E. This will be P e to the power minus V. And this is 1 by E. This is 1. This is 2. So calculate for this. This is the most difficult type of the sum you can be expecting. This came in some IIT paper. Okay. Just try once. See, what is being said here? This image shows you a PV diagram, okay? This image shows you a PV diagram. This is P, this is V. So we are saying this is a PV diagram with points A, B, and C. So the process appears to involve an ideal gas, okay, undergoing changes in pressure and volume. So our goal is to calculate the work done during this process. Assumptions, what we are assuming, ideal gas, that the gas behaves as an ideal gas, so it will follow the PV is equals to nRT path. Okay, since here it is written PV and no other information is given, because if we can't consider it to be an ideal gas, we can't solve the question. So we have made that assumption. And the path from A to B is not specified, but we will assume it that it is a reversible process, either isothermal or adiabatic. So in this problem, we have made two assumptions. First assumption is that it is an ideal gas. So it is following the PV path, okay? And second is the path from A to B is not specified. Path from A to B is not specified. But we will assume it's a reversible process. Either isothermal or adiabatic. Up to this clear? Okay. So work done. First, we will be calculating for work done. So work done. So work done in a thermodynamic process is given by the area under the PV curve, right? So from the diagram, we can calculate the work done in three parts. AB in, we have considered AB is a reversible process. So the work done can be calculated by using, so work done in AB will be calculated like how? Integral of P dV, yes or no? From A to B. Okay. Now the exact expression for this integral depends on the specific path, isothermal or adiabatic. Now BC. BC is work done, BC is being said that it is done at a constant pressure. See, the pressure has not changed. Value of a pressure is given. Okay, so the pressure is constant for BC path. So this is a constant pressure process. Means this is BC path is isobaric. These are the small hints you will be getting during your exam. So this is isobaric. So the work done will simply be, what will be the formula? P del V. That is P of okay, and again CA. This is a constant volume process. So this is a constant volume process. So okay, so this will be isoporic. Okay, so here what will be the thing? Isoporic. So WCA is 0. Because in isoporic process at a constant volume, no work is done. Okay, so the total work done, what will be that? Okay. Now, if we start considering the values, like this point, now you will be just putting those values. Yeah, so like PA, PB, that is 2P0. VA, VB is V0. VC is equals to 2V0. Okay. Now work done at W is equals to AB is equal to equivalent to, you will be just putting VA by VB. Since here the integral parts are given, you can use that also. Okay. So accordingly, you can just put these values are just to represent this. Isoporic, isobaric, and so on. These specific values will be given to you during your exams. So accordingly, just put those values and thus solve. Okay. Okay. This is something for this question. Okay. Now, I guess all the processes have been done. We have done all the process. Okay, something I need to discuss for your boards is limitations of first law of the thermodynamics. What are the basic limitations? It helps in determining energy exchange in terms of heat and work, but it does not determining heat exchange. In terms of eat, and work. But it does not tell us anything about feasibility of the process. What is feasibility? We will be learning in the second law of the process. And also it does not tell us about the extent of a process. Okay, so these are the two basic laws for the two basic flaws basically. Two basic flaws for first law of the thermodynamics. Is this the first law of the thermodynamics clear? I know I have done some very difficult concepts for the first law of the thermodynamics, but it is fine. That they may not be coming in your exams, but otherwise I guess that will be fine for you. Okay. Now, can we just start the second law of the thermodynamics? We will be doing with the entropy and enthalpy and those things. So let's start with the second law of the thermodynamics. We will just do the basic things for the second law of the thermodynamics. So according to the second law of the thermodynamics, it is impossible to build a cyclic machine operating in between two temperatures which can convert 100% heat given to it at a higher temperature into work without liberating same amount of heat at the lower temperature. In easy words, there is a natural asymmetry between heat and work. So 100% work can be converted to 100% heat, but 100% heat cannot be converted to 100% work cyclically. So this is the second law of the thermodynamics, but modern researchers say that the second law of the thermodynamics have been proven wrong. Okay, so it is just being said that now the second law of the thermodynamics has also been proven wrong. Basic definition you can know from your book. I am just saying the interpretation. What is the interpretation? There is a natural asymmetry between heat and work. 100% work can be converted to heat, but 100% heat cannot be converted to work cyclically. This is something the easy interpretation of the second part or second law of the thermodynamics. Okay, so now we will be now imagine the best example for the cyclic. Best example is the cyclic process. Now we will consider Carnot engine, which is based on the Carnot cycle. So what is Carnot cycle, Carnot engine? Let's do this. So what is the heading? Carnot cycle. Okay, so it considers the 4 reversible process, out of which the 2 of them are reversible isothermal and 2 are reversible adiabatic. Okay, so it consists of all the 4 reversible process, out of which these 2 are reversible isothermal and 2 are reversible adiabatic. Okay, just remember this. So work done in the Carnot cycle is not work done. This represents, this we call as eta. So eta in the Carnot cycle represents work done by heat supplied. Okay. So what is the work done? Obviously negative. In positive. So QH is heat supplied to the system. QL is heat removed from the system. And W is the work done. Okay, so efficiency of the Carnot cycle is independent of this working substance, but we will consider ideal gas as our working substance. Okay?
Ma'am,
Yeah, say.
can you tell me why did you take work as a negative one?
Yeah, just repeat.
Why did you take work down in negative, ma'am?
Okay, good question. Can anyone answer me why it is being taken as negative? Anyone? Anyone from the class, can anyone tell me why the work done is being negative here?
Ma'am,
Yeah, say.
I don't think it was right. I think it is released, energy is released, that's why we had taken it is negative. Is that it, ma'am?
So what you are saying? Just repeat once.
The energy is released, that's why we had taken it as negative.
If I say like that, the work done is taken negative in the Carnot cycle because it is conveniently like it is being convenient. What I will say that I am not getting the proper term. It's not conventional. Uh, like the work done is, it is being considered that in a Carnot cycle, work is done by the system on its surrounding. So if the system does work, like I mean to say that the Carnot engine is doing the work. So in other words, I can say that our Carnot engine does the work on its environment. But if the environment is doing the work on the system, we are considering it as the negative. In Carnot cycle, what happens? The system is the heat engine. So heat engine does the work on the surroundings by converting heat into mechanical energy. So the work done is negative. Okay, indicating that the energy is leaving the system. This is a good question. I am writing it here also. That if the system does work on surrounding, system does work on surrounding, what we get? System does work on its environment, we consider it to be positive. But environment is doing the work. Yes, we are considering it positive. But if the environment does the work on the system, then the work is considered to be negative. Like environment does the work on the system, we consider it to be negative. In the Carnot cycle, the system, that is the heat engine, does the work on the surrounding. Okay, by converting the heat into mechanical energy. So it's the negative work done. Means energy is leaving the system. I've written it opposite. I've written opposite here. In Carnot cycle, system is heat engine. Heat engine does work on the surroundings, converting heat into mechanical energy. Thus, heat is being removed. Thus, what happens? Q is considered to be negative. Is this part clear? Not Q, work done is considered to be negative. Okay. In the thermodynamics, the main problem is that you don't know a lot of stuff. You don't know what is a Carnot cycle. You don't know what is a Carnot engine. These are the things you will be taught in the first semester of your, first semester of your engineering also. There you can understand in more details. But since our time is limited, I can't tell you about what is Carnot cycle, what is Carnot engine. So then these problems will not arise in your head. Why is this? Why is that? So thermodynamics is kind of memory based plus boring chapter, plus you don't know a lot of things, so you don't get to understand a lot of things. Okay, so these are the different things that happens. Okay, so let's just move to the next part. So what is isothermal process? What is an adiabatic process? What is isothermal expansion? What is the adiabatic expansion? Can anyone tell me? See, efficiency of a Carnot cycle is independent of work done, of the working substance. Of the working substance. But we will still consider our working substance to be an ideal gas. Because see, if we consider it to be an ideal gas, we can use that PV is equals to nRT formula, 3/2 nRT formulas in our question. And since our Carnot cycle is independent, like it is not hampered that whether you are using ideal gas or normal gas or anything. So we can be using the ideal gas to solve our calculation and can also calculate the efficiency of the Carnot cycle. So this is just like a tips why we are using what and when. Is this part clear? If something is going overloaded or over your head or something, you can tell me. I know this part is quite difficult. This part is actually quite difficult. I know. So up to this, is this part clear to everyone? If not, just ask me question. Up to this, any doubt, anything? Because if I move to the next part, you don't understand, then that will be a great problem, great problem. So just ask me now only. Does anyone have any problem? Yes.
Once.
Yeah, say. Okay, good. No one has no problem. It's either I am teaching quite good than I should, or
Ma'am,
else, yeah.
someone is asking that can you explain it once again?
I can't hear you properly.
Ma'am, someone is asking that can you explain it once again?
Yes, good. Finally. See, what is the second law for the thermodynamics? Second law for the thermodynamics states that till now, till the first law, we were dealing with heat, work, and everything. So 100% of the work can be converted to heat, but 100% of heat cannot be converted to work cyclically. This is what being said according to second law of the thermodynamics. And to prove this hypothesis, what was done? Carnot cycle was taken. So this is the efficiency of the Carnot cycle. Work done by heat supply, and then this convention was done. Someone asked us why the negative is taken. I told you that in a Carnot cycle, system is the heat engine. In the heat engine does the work on the surroundings. So heat is to be measured. So heat is being removed from this system. So W is taken as negative. Okay. Now, I told you that the efficiency, this eta part can't be calculated, does not depend on the working substance. Like in the heating machine, if you are putting petrol or an ideal gas, it does not care. Efficiency will be same for everyone. So while but we can't calculate the efficiency by putting petrol, right? Do we know the formulas? What formulas do petrol uses and so on? Do we? No. So we don't do that. What we do is that we consider it as an ideal gas. So the efficiency of the Carnot cycle is independent of the working substance, but we do the ideal gas. So the ideal gas, since we know many formulas for ideal gas, PV is equals to nRT, 3 by 2 nR delta T and so on. So accordingly, we will be just using this and then calculate the efficiency of the Carnot cycle. Is this part clear, everyone? Till now, is this part clear now?
Yes, ma'am.
Okay. So I guess you are facing problems because you don't know a lot of things. From tomorrow, I don't know, tomorrow maybe I am taking today Himanshu sir's class. So I don't know, maybe he will take tomorrow's class, whatever. From the next class, I will be teaching you from something more basics, okay? So that you can be actually sure of what is happening in the surroundings, what is not. And you won't be facing doubt. So first law, till this today, start revising the first law. Give me the doubts from the first law, because then we will be moving very much confidently to the second law of the thermodynamics. Is this part clear in extreme details? Are we good now? Okay? Yes or no? Okay or not?
Okay, ma'am.
Okay
Yeah.
then. Ma'am, this was from my part.
Ma'am, Arun sir.
Yeah, you can start joining the next class.
Join the next session, students. Thank you, ma'am.
Thank you, sir.
Thank you, ma'am. Students, you can join the next session.